This webcast discusses Newton's universal law of gravitation. A gravitational force exists between any two particles that have mass in the universe. No direct contact is required. The gravitational force is an action at a distance type of force. This gravitational force always causes the two objects to attract one another. That means that they pull toward each other. And by Newton's third law, the two masses exert equal but opposite forces on each other, and those forces act on a line that between the centers of the two objects. So here is an example of the Earth exerting a gravitational force on the moon. And so from the center of the Earth to the center of the moon, if you imagined a line connecting those two centers, the forces are acting along that line. The Earth is exerting a force that tries to pull the moon toward the center of the Earth, and the moon exerts a gravitational force that tries to pull the Earth toward the center of the moon. This force is proportional to the product of the two masses. You'll notice that we're using an uppercase M to represent the larger mass and a lowercase m to represent the smaller of the two masses. The force decreases with the square of the distance between the two, and we're using the letter R to represent that distance between the two masses. In this case, R is, just don't confuse R with radius. R is the distance between the two masses. And these two forces have the same magnitude, but they have opposite directions because they are Newton's third law pairs of forces. So Newton's law of universal gravitation says that the attractive force, it's called attractive because, remember, the two objects try to pull toward each other. The attractive force of gravity between two particles is proportional to the product of their masses and inversely proportional to the square of the distance between them. And so in equation form, the gravitational force equals the universal gravitational constant, that's represented by the uppercase G, multiplied by the product of the two masses. Here we're using an uppercase M to represent the larger mass, and the lowercase m to represent the smaller mass, divided by R squared, where R is the distance between the centers of the masses. The gravitational constant, G, has a value of 6.67 times 10 to the negative 11th. Because that gravitational constant is so small, notice it's times 10 to the negative 11th, that means that at least one of the masses must be very large on a celestial scale, such as a planet or a sun or a star. At least one of those masses must be that large in order for the gravitational force to be a very significant number. So as example, let's talk about the gravitational force that the Earth exerts on the moon and that the moon exerts on the Earth. So we have their two masses, and they are both large. The Earth's is larger, but the moon also has a lot of mass, and we know their average distance is 3.84 times 10 to the 8th meters. And so we could calculate the gravitational force, and we would find that it's 1.98 times 10 to the 20th newtons. That's a large amount of force, almost 2 times 10 to the 20th. Now, let's consider how much gravitational force exists between a car and a truck at about a 15-meter distance. I mean, these are both fairly large objects in our world. We can't pick them up. They have a lot of mass. But when we calculate the gravitational force between the car and the truck, we find that it's only about 0.7 newtons, so much, much smaller. And again, that's because that gravitational constant is so small, and so at least one of the objects must be on a very large scale, like a planet or a star, in order for FG to be very large. So uppercase G represents the universal gravitational constant, and this value is the same everywhere in the universe. It's always 6.67 times 10 to the negative 11th. Lowercase g is the free fall acceleration due to gravity. And a lot of times we work with this lowercase g as if it were a constant, but really this acceleration due to gravity changes depending on location in the universe. So, we are usually close to the Earth's surface, and at that location, g is 9.8 meters per second squared. But if we were to go to the moon or Mars or anywhere else very far away from the surface of the Earth, we would see that g is very different. And so let's just take a look at how gravitational force changes as distance from the Earth increases. And so in order to show an example of that, we'll consider the gravitational force exerted on a student in two situations. First of all, when the student is standing at sea level on the surface of the Earth, and second, when that student is up in a plane that is 12,192 meters above the surface of the Earth. So here we've got a picture. The white arrow shows the R, basically the distance between the student and the center of the Earth when the student is at a position at sea level, and the longer yellow arrow represents the distance between the student and the center of the Earth when the student is in the airplane. And they are different. So to find the force of gravity on someone when they're on the surface of the Earth, r is the radius of the Earth. But when we want to find the force of gravity on someone in an airplane, then that r is the sum of the Earth's radius plus the altitude of the airplane. And so so we have to take the radius of the Earth and add that altitude to it. Okay, so we're going to look at this in two ways. So when the student is at sea level, their mass is 70 kilograms, and so if we use the force of gravity equation, we can find that that force of gravity acting on them when they are at sea level is 686 newtons. But then, if we're going to look at them in an airplane, and we see that the force changes just a little bit. Because the r is now the radius of the Earth plus the altitude, we are dividing by the square of a larger number, and that means that the gravitational force is smaller. Now, these two numbers are not dramatically different. One is 686 newtons, one is 684, but they're just starting to move away from the center of the Earth. Okay, we can also talk about acceleration due to gravity. Remember, that is what we use the symbol lowercase g to represent. So acceleration due to gravity means that an object in free fall is moving only under the influence of the gravitational force. So other forces such as drag force can be ignored because they are so small, they are negligible. In this situation of free fall, the acceleration is called acceleration due to gravity. It's represented by that symbol g, where g, it's a lowercase g. this value of acceleration is different at different locations in the universe. And acceleration due to gravity will get smaller as distance from the Earth increases. So, we have an equation to calculate the gravitational force, which is G(m)m over r squared. But we could also calculate that gravitational force by taking the mass of the object and multiplying it by the acceleration due to gravity. We've been doing that all year when we make force diagrams. And we find the weight of the object, or the force of gravity acting on the object, by taking the mass and multiplying by g. So if we make those two things equal to each other, then we see that there's a formula for acceleration due to gravity, which is the universal gravitational constant times the mass of the planet, the mass of the Earth, divided by the distance between the object and the center of that planet squared. So as the distance from the center of the Earth, as that r increases, the acceleration due to gravity will get smaller. And so let's find the acceleration due to gravity that is acting on that student, both when they're at sea level on the surface of the Earth and also when they're up in the airplane. Okay, so at sea level, the acceleration due to gravity is 9.799 meters per second squared. In this case, we're using r. The r is the radius of the Earth. We're using to calculate that g. If in the airplane, the r is the radius of the Earth plus the altitude of the airplane. So it's a little bit bigger. And so then when we calculate the acceleration due to gravity, we get 9.762. Notice that we did have to keep enough digits, to really be able to see that difference, because it is small when the difference in the r is not too large. But g is starting to get smaller as you move in the airplane, and so if you moved up to the space station or halfway between Earth and the Moon, g is going to keep getting smaller and smaller the further you get from the center of the Earth. So why does the free fall acceleration not depend on an object's mass? Because we can see that the gravitational force that the Earth exerts is larger for a larger mass than it is for a smaller mass. But we've learned that the rate of free fall acceleration is supposed to be constant and not depend on the mass. Well, if we look at Newton's second law, we know that acceleration is proportional to the net force, and it's inversely proportional to the mass. And so even though the net force, which is the force of gravity on an object in free fall, is larger for a larger mass than for a smaller mass, we're dividing by the mass, and so you're dividing by a larger number. And so therefore the acceleration really is constant for objects of any mass.